As large as a hurricane is, its behavior is subject to subtle shifts in wind and ocean currents, the presence of land masses, and the interaction of all the clouds and water molecules, and even dust entrained within it. Scientists are zeroing in on a few key diagnostics to predict when and where a storm might intensify and threaten human lives and property. One of them is the warmth of the ocean out ahead of the storm, the fuel that hurricanes thrive upon. Because hurricanes can draw huge volumes of water up from the deep, this warm surface layer must be thick for the storm to reach high intensity. An Atlantic hurricane often begins its life over the mountains in East Africa, as an area of low pressure. It travels across the Sahara Desert, then moves out over warm ocean waters. Traveling with the trade winds that circle the globe just above and below the equator, these lows can spawn thunderstorms over a broad region. They gradually come under the influence of the Earth's rotation, called the Coriolis force, and begin to spin. At the center, a region of low atmospheric pressure forms, known as the eye. It acts like a partial vacuum, causing winds at the sea surface to spiral inward toward it. These in-spiraling winds evaporate moisture from the warm ocean surface. As they near the eye, they rise rapidly, producing clouds and rain. Much of the air flows outward at the top of the storm, like a chimney. Some flows back down into the eye itself, causing this central zone to dry out and become clear. When Hurricane Katrina entered the Gulf of Mexico in 2005, it encountered a wide and deep tongue of exceptionally warm water that originates in the Caribbean, called the loop current. As Katrina moved over this current, its winds picked up speed, reaching 175 miles per hour, Category 5 status. At the same time, a series of individual storms literally exploded within the main storm. You can see them in this sequence of satellite images. This often happens when the eye of the storm, the central region, contracts, getting smaller. The winds moving around the eye accelerate. Eddies or vortices begin to develop. These vortices cause huge amounts of moisture to evaporate from the ocean surface. Rapidly growing clouds then expand and shoot to the top of the hurricane. A computer simulation recreates the flow within these convective towers. As air from the surface accelerates upward, it pulls more air up from behind it. Because these clouds can be spotted as they first develop, they are a sign that things could really be heating up. In Katrina, the growth of these so-called hot towers coincided with its rise to super hurricane status. It also coincided with a fierce battle that had begun to develop deep within the storm itself. In this satellite image, a microwave beam was used to slice through Katrina at the point of maximum intensity. Convection had intensified not just around the eye, but further out as well. Even as the eye wall forms, conditions are often so favorable for hurricane development that a second eye wall begins to form around it. The larger eye wall sweeps up moisture from the sea, fueling a new set of towers, and sending clouds spiraling out the top. From there, the outer eye contracts and takes its place. This cycle helps explain Katrina's behavior on the way to New Orleans. The tools scientists are now using to study and predict the behavior of hurricanes are more varied than ever. Rainfall rates, lightning strikes, convective towers, the battle of the eye walls. These factors evolve with changing conditions in the storm environment. It's not surprising, then, that the more we learn about how hurricanes work, the more complicated this environment seems to become.